Just confirm me audio video is clear to you. Just confirm whether audio video is clear to you or not. Just confirm whether audio video is clear to you. So a very good evening everyone. Myself Prateek Mishra and I welcome you all to the YouTube platform of IMS GATE Academy. We are conducting this session for most excellent questions that are expected in GATE 24 and I'll be dealing with environmental engineering, right? Parallelly, we are taking up these two series. One is with the most expected concept and second one is the excellent practice questions, okay? So in these sessions, we are basically dealing with those questions which are basically hard to understand by a student who is preparing for GATE examination. So our sole aim is to make you aware about the different varieties of questions that can be framed from a particular topic, and also in this just a span of one and a half hour. The sole motive is to make you practice a lot of concepts. Okay, so we will start with the topic of treatment of raw water, and in this session we will going to see the most expected concepts from this topic. Okay, so let us start with this. Okay, while we were dealing with this question, I'll give you the question, even I'll give you the time of 2 minutes or 3 minutes. You can attempt that question, and after that we will going to answer and understand what that question means and how to solve this in a very less time. Okay, so let's shoot this first question, attempt this first question. This is from the topic of coagulation and flocculation. Just try this one. I'll set up the timer for you also. There is a timer for 2 minutes, right? Please start attempting this question. This is the question from coagulation and flocculation, and again a very, very important concept. Please try to solve this. Keep answering whatever things you are getting, keep answering straight away. Okay, time's up. Let's solve this. Question says that a flocculator tank has a volume of 2800 meter cube. The temperature of water in the tank is 15 degrees Celsius. Next. And an average velocity gradient is maintained in the tank is 100 per second. So let us write this data first. So volume of the tank is volume is given as 2800 meter cube. Temperature is 15 degrees Celsius. And G at 15 degrees Celsius. Remember, temporal mean velocity gradient. It means this temporal mean velocity gradient represents the intensity of mixing in the flocculation tank. So G is given as 100 per second. Okay, next. The temperature of water is reduced to 5 degrees Celsius. So from 15 degrees Celsius, the temperature of water is reduced to 5 degrees Celsius. When the temperature of water is reduced, the dynamic viscosity or the viscosity of water will going to increase, right? For the same amount of power given to this water, the intensity of mixing will be less. You can just take an example. At 15 degrees Celsius, there is some viscosity of this water. When you reduce the temperature of this water, the resistance offered by this water will going to increase. Dynamic viscosity will going to increase, okay? But all the other operating conditions, including the power input, are maintained as same. The power that you are using to go for flocculation is maintained same. The decrease in average velocity gradient in percentage due to reduction in temperature is rounded off to nearest two integer places. The dynamic viscosity of water at 15 degrees Celsius and 5 degrees Celsius are given to us. So we will write all the data. Okay, so G is given to us, then dynamic viscosity at 15 degrees Celsius is given to us as 1.139 into 10 raised power minus 3. This is 1.139 into 10 raised power minus 3. And the unit is Newton second per meter square. This is Newton second per meter square. The temperature is reduced, T2, it is reduced to 5 degrees Celsius. And dynamic viscosity at 5 degrees Celsius is equal to 1.518 into 10 raised power minus 3. 1.518 into 10 raised power minus 3 Newton second per meter square. Okay. So what I said is, when you reduce the temperature of the water, the dynamic viscosity of the water will increase. Means the water or that fluid will become more thick. A very good evening Amit sir. When the temperature of the water will decrease, the dynamic viscosity will increase. Means for causing same intensity of mixing, you need to supply more power. Or if you are supplying same power at 5 degrees Celsius and 15 degrees Celsius, the intensity of mixing at 5 degrees Celsius will be less. So power supplied at 15 degrees Celsius is equal to the power supplied at 5 degrees Celsius. Now when we have talked about the intensity of mixing, this parameter G, this temporal mean velocity gradient Gs, it is defined as under root of P by mu into V, where P is the power of the shaft, mu is the dynamic viscosity of fluid, and V is the volume of the flocculation tank. From this expression, it is clearly visible that if you increase the power, intensity of mixing will increase. But if you increase the dynamic viscosity, intensity of mixing will decrease. And that is what asked in the question. When you reduce the temperature, by how much amount this intensity of mixing will reduce, right? So we will use this. Power at 15 degrees Celsius is equal to power at 5 degrees Celsius. When you just reduce this expression, the power expression will be P is equals to Gs square into mu into V. This is the expression for power. So G at 15 degrees Celsius we know. If we know G at 5 degrees Celsius, we can calculate the decrease in intensity of mixing. So we will start with this. Power supplied at 15 degrees Celsius is equal to power supplied at 5 degrees Celsius. Power supplied at 15 degrees Celsius, power supplied at 15 degrees Celsius is equal to G at 15 degrees Celsius whole square into mu at 15 degrees Celsius into volume of the tank. Since volume of the tank is not changing, it is same 2800 meter cube, right? This is equal to G at 5 degrees Celsius square into mu at 5 degrees Celsius into volume of the flocculation tank. This V and V will going to cancel out. Now just substitute the value of G at 15 degree. So this is 100 square multiplied by mu at 15 degrees Celsius, which is 1.139 into 10 raised power minus 3. 1.139 into 10 raised power minus 3. This is equal to G at 5 degrees Celsius whole square multiplied by mu at 5 degrees Celsius, which is 1.518. This is 1.518 into 10 raised power minus 3. From here you can calculate the value of G at 5 degrees Celsius. Just do the calculation quickly. Even I am solving it with you today, right? So we will start with this. So this 10 raised power minus 3 and 10 raised power minus 3 will going to cancel out from the either side. You have 1.139 divided by 1.518. You take under root of this and you multiply it with 100. So this comes out to be 86.62. G at 5 degrees Celsius comes out to be 86.62 per second. Okay. Now you know the value of G at 15 degrees Celsius. You know the value of G at 5 degrees Celsius. You can calculate the percentage decrease. So percentage decrease in intensity of mixing this is equal to G at 15 degrees Celsius minus G at 5 degrees Celsius divided by G at 15 degrees Celsius into 100. So G at 15 degrees Celsius is given as 100. G at 5 degrees Celsius we have just now calculated 86.62. This is 86.62 divided by 100 and multiply by 100. So from here directly you will get the value of percentage decrease. So this is 100 minus 86.62, which comes out to be 13.38%. This comes out to be 13.38%. This is the percentage decrease in the intensity of mixing, and this was asked in the question, right? The same type of question was asked in GATE 23 for 2 marks. So when we talk about coagulation and flocculation, my dear students, there are 2 important topics. First one is the type of coagulant and which type of coagulant will produce how much kind of sludge, how much amount of sludge. And second is from this intensity of mixing. Intensity of mixing GS is equals to under root of P upon mu into V. P is the power provided to the shaft, mu is the dynamic viscosity and V is the volume of the flocculation tank. Okay. So this is our first question. Chalo. Moving on with this, just try this one. This was the question from sedimentation. Try this one. Again, I'll keep the timer and this time it will be like 1 minute. It is and your time starts now. Just try this one. Just try this one. Okay, time's up. Let's start with this. The question says that a water treatment plant has a sedimentation basin of depth 3 meters, width 5 meters, and length is 40 meters. You have a sedimentation tank for which the dimensions are given to you. The next thing that is given to you is the water inflow rate is 500 meter cube per hour. That is the discharge that is entering into the sedimentation tank is 500 meter cube per hour. The removal fraction of particles having the settling velocity of 1 meter per hour is. Okay. So first of all, when we talk about sedimentation, the first thing is all the sedimentation tanks are designed for the removal of concerned size of the particle. If the size of the particle is equal to the concerned size or more than the concerned size, they will be 100% removed. But particles which are having small size, less than the concerned size, they are partially removed. So for those small sizes of particle, this question is framed. You need to calculate the percentage removal of the smaller size of particle for which the settling velocity is 1 meter per hour. Right? You understand this? You need to calculate the percentage removal. You need to calculate the percentage removal of this smaller size of particle for which the settling velocity is 1 meter per hour. So settling velocity of this small size of particle Vs1 is 1 meter per hour. So percentage removal is Vs1 divided by Vs into 100. Now this Vs is nothing but the settling velocity of the concerned size of the particle for which this sedimentation tank is designed. This settling velocity is also known as the surface overflow rate. So I'll just write down here. Vs is settling velocity of concerned size of particle for which this sedimentation tank has been designed. And this Vs is also known as surface overflow rate. This Vs is also known as surface overflow rate, SOR. For calculating this percentage removal, we know the value of Vs1. If anyhow we can determine the value of Vs, that is surface overflow rate for this tank, it is very easy to calculate the percentage removal, right? Now this surface overflow rate, Vs, surface overflow rate, Vs is equal to design discharge or discharge which is entering into the sedimentation tank divided by the plan area. Divided by the plan area, right? Discharge which is entering into the tank, it is given to us 500 meter cube per hour. Even plan area we know by observing these dimensions. Depth of the tank is 3 meter, width of the tank is 5 meter, and length of the tank is 40 meter. So plan area will be width by length. Width is 5 meter, length is 40 meters. So from here we can calculate the surface overflow rate. So this is the tank given to us. I'll draw here. This length is 40 meters. Depth is 3 meter and width is 5 meter. This depth is 3 meters. And this width is 5 meters. So from here clearly the plan area is visible. Plan area is 5 meter by 40 meters. Plan area is 5 meter by 40 meters. And discharge is also given to us. Discharge is how much? It is 500 meter cube per hour. This is 500 meter cube per hour. Now in this type of question, my dear students, you should keep a special check on the units, right? Because these type of easy concepts are asked to check how carefully you are observing the units. So every time you are substituting the value of Vs1 and Vs, please keep a check that unit of Vs1 is same as that of Vs, right? That is the only trick which is played in these type of questions. Okay, so inflow rate is 500 meter cube per hour and the settling velocity of the smaller size of particle is given as 1 meter per hour. Settling velocity Vs1 is given as 1 meter per hour. So first of all, calculate Vs. Vs is nothing but surface overflow rate and which is equal to discharge divided by plan area. Discharge is how much? Discharge is 500 meter cube per hour. I will write all the units, 500 meter cube per hour. And plan area is how much? Plan area is 5 into 40. This is 5 into 40. And this is in meter square. So from here, whatever surface overflow rate or settling velocity of the concerned size of the particle you will calculate, that will be in meter per hour. Just quickly do this calculation. So this is 500 divided by 200. So this Vs comes out to be 2.5 meter per hour. This is the settling velocity of the concerned size of the particle for which we have designed the tank. Now calculate the percentage removal. Percentage removal of smaller size of particle is Vs1 divided by Vs into 100. Vs1 is how much? It is 1. Vs is 2.5 into 100. From here you can calculate the percentage removal, right? So percentage removal I think comes out to be 40%. This comes out to be 40%. Percentage removal comes out to be 40%. These type of questions are asked for many times, right? It is like you will see repetitive questions in GATE from this concept related to the percentage removal of smaller size of particle. Usually what happens with the student is they confuse themselves with different sizes of particle. First of all, you need to be clear on this. Every time you are designing a horizontal flow type sedimentation tank, it is designed for the removal of concerned size of particle, which is one size. Okay. All the particles which are having size equal to or more than the concerned size will be 100% removed, and the particles which are having less size than the concerned size, those are partially removed. And this is how we calculate the percentage removal for smaller size of particle. Okay, so I hope this is clear to you. Chalo, moving on with the next question. This is the question from filtration. Again, I'll keep a timer. This time I'll keep a timer for 3 minutes. You try this. It's a very, very important type of question. This time I keep the timer for 3 minutes. You try this. Okay, so time's up. Let's solve this, right? Now, this question is one of the example of how the questions are made complicated, right? When these people who are making these questions for GATE examination, they just stuff so much of data that a student gets confused, right? How to approach to the question. My sincere advice to these type of questions is, whenever you are reading these type of questions, the first thing is, please break the questions into small fragments and try to understand what is asked in the question. Okay, so we will start with this. This is the question from filtration. Question says that a water filtration unit is made of uniform size particle. Okay, means it is talking about a gravity filter. It can be a slow sand filter or rapid sand filter. Till now we do not know. Okay, because in gravity filters basically we use uniform size particle. Next is particles of 0.4 mm diameter with shape factor of 0.84 and specific gravity of 2.55. So this is the detail given to you about filter medium that they are using. Next, the depth of the filter bed is 0.7 meters and porosity of this filter bed is 0.35. Depth of the filter bed is 0.7 meters and porosity is 0.35. The filter bed is to be expanded to a porosity of 0.65 by hydraulic backwashing. Okay, now here comes the question, main question. So basically they are talking about rapid sand filters, and these rapid sand filters are cleaned using backwashing. Basically we send this compressed water, right, means water with very high pressure from the back side of the filter, so that this filter bed can expand and all the impurities can come along with the backwash water. So you need to understand this picture. Initially this is my filter bed. Initially this is my filter bed like this. This filter bed contains impurities and these impurities penetrate for the full depth of the filter medium, right? These impurities penetrate to the full depth of the filter medium, and this is the picture for rapid sand filters. In order to clean these filters, basically we send water at very high pressure from the bottom. And while we are sending this water with very high pressure from the bottom, this process is known as backwashing. Okay. So this is my initial picture of the filter bed, the depth of the filter bed and porosity of the filter bed. So depth is D, porosity of the filter bed is eta. So this is porosity of unexpanded bed. So this porosity of unexpanded bed is given as 0.7, it is given as 0.35. It is given as 0.35. This depth of filter bed, unexpanded filter bed, this is given as 0.7 meters. Okay. When you send this backwash water to this filter medium, the porosity of the filter medium will increase, means particle of the filter medium will separate out like this. The particles of the filter medium will going to expand like this. They will going to expand like this. Now you can clearly see from this picture that depth of the filter medium has increased. Earlier it was this. Now this is the depth of the filter medium. And since the volume of voids is increasing, due to which porosity of this expanded bed also increases. This is your D dash. Depth of the expanded bed. And porosity of the expanded bed even increases. So this porosity of expanded bed, eta expanded. Now this is also given to us. The porosity of the expanded bed is 0.65. You can clearly see from this. From 0.35, this is increased to 0.65. And all this backwash water like this, which is flowing from the bottom, it will take away all the impurities which is present over the or between the filter medium. It will take away all the impurities which are present inside the voids of the filter medium like this. It will take away all the impurities which are present inside the voids of the filter medium. So when you are sending backwash water, this backwash water is cleaning the filter medium by taking away all the impurities. Okay. The settling velocity of the filter medium particle is given to you. The terminal settling velocity of the sand particle during backwashing is 4.5 centimeter per second. So settling velocity of the filter medium particle. This is filter medium particle. This is how much? 4.5 centimeter per second. This is 4.5 centimeter per second. And you are asked to calculate the backwash velocity, that at which rate we are sending this water for backwashing. You are asked to calculate the backwash velocity. Now there is one simple relation for calculating this backwash velocity. There is the relation between porosity of expanded bed, settling velocity of the sand particles or the medium particles, and the backwash velocity. And that expression is porosity of expanded bed. Porosity of expanded bed is equal to backwash velocity VB divided by the settling velocity of the filter medium particle raised to the power 0.22, where VB is the backwash velocity. It is the backwash velocity. And Vs is the settling velocity of the medium particle. Porosity of expanded bed is equal to 0.65. This is equal to Vb, that I need to calculate, divided by velocity, settling velocity of the medium particle, which is 4.5 centimeter per second. This is 4.5 centimeter per second. Please take care of the units. Raised to the power 0.22. From here you can calculate the backwash velocity. Just do the calculation. Even I'll do the calculation here. Just do the calculation for this. So this is, you take log on both the sides, right? Or you can directly take 0.65 raised to the power 1 divided by 0.22 multiplied by 4.5. Okay, so this comes out to be, from here VB comes out to be 0.635 in centimeter per second. This is the value of VB, 0.635 centimeter per second. Please check on the units. Now check on the options that are given to us. So 6.35 into 10 raised per minus 3 meter per second. Okay, so we will convert this. VB is equal to 0.635 centimeter per second. So same thing I can write down as 6.35 into 10 raised power minus 1 centimeter per second. When you convert this centimeter into meters, so you have to divide by divide by 100. So this is 6.35 into 10 raised power minus 3 meter per second. You have to divide by 100, so it will be 6.35 into 10 raised power minus 3. So for this question, option number D is the correct answer, right? So these type of simple questions are framed when we talk about the topic of filtration. The only thing is they will going to bombard so much of information that you will going to forget what is actually asked in the question. It is again one of the favorite questions for GATE examination. Chalo, moving on with this. Try this one. This is the question from sedimentation. Again, I'll give you a timer for 2 minutes. Try this one. And your time starts now. Please do with this. Okay, time's up. Let's solve this. So this is the question again from the topic of sedimentation. Question says that the surface overflow rate of a primary settling tank in which discrete particles settling is 20,000 liter per meter square per day. First of all, I'll write down the data. Surface overflow rate for this sedimentation tank is 20,000 liter per meter square per day. Okay. This is the surface overflow rate. Let me check it again. Yeah, this is 20,000 liter per meter square per day. Okay. What is surface overflow rate? I'll again repeat myself. It is the settling velocity of the concerned size of the particle for which we have designed the sedimentation tank. Okay. Next. Kinematic viscosity of water in the tank is 1.01 into 10 raised to power minus 2 centimeter square per second. Again, I'll write this. Kinematic viscosity of water is 1.01 into 10 raised to power minus 2 centimeter square per second. 1.01 into 10 raised to power minus 2 centimeter square per second. So when you convert this into meter square per second, this will be 1.01 into 10 raised to power minus 2. When you convert centimeter square into meter square, it will be 10 raised to power minus 4. So this is 10 raised to power minus 2 multiplied by 10 raised to power minus 4 meter square per second. Similarly, when you take this surface overflow rate in 20,000 liter per meter square per day, you convert this liter into meter cube, so you have to divide by 1000. So in that case, this surface overflow rate comes out to be 20 meter cube per meter square per day. And this is nothing but the settling velocity of the concerned size of the particle for which we have designed the tank, Vs. Next. Specific gravity of the settling particle is 2.64. And acceleration due to gravity is 9.81 meter per second square. The minimum diameter in micrometer rounded off to 1 decimal place of the particle that will be removed with 80% efficiency. So basically the question is asking that size of the particle which is smaller than the concerned size and which will be removed with 80% efficiency. That is, the percentage removal of the smaller size of particle is given as 80%. Percentage removal of smaller size of particle, percentage removal of the smaller size of particle is given as 80%. Now this percentage removal of the smaller size of particle is equal to settling velocity of the smaller size of particle divided by the surface overflow rate into 100. The surface overflow rate is nothing but the settling velocity of the concerned size of the particle, okay. So if anyhow I know this Vs1, that is the settling velocity of the smaller size of particle, using the expression for settling velocity I can get the size of that particle. So step 1 is to calculate the settling velocity of the smaller size of particle. So percentage removal is 80%. So I will write 0.8 is equal to Vs1 divided by Vs. Vs is 20 meter cube per meter square per day. So this comes out to be meter per day, right? You just calculate this Vs1. Vs1 comes out to be 16 meter per day. Now convert this meter per day into meter per second. So this will be how much? 16 divided by 3600 into 24. This is the settling velocity of smaller size of particle in meter per second. So Vs1 is 16 divided by 3624 meter per second, okay. Now using the expression for settling velocity, so Vs1, so if I say let the size of smaller particle be d1. This is the size of smaller particle. So settling velocity Vs1 of the smaller particle is equal to 1 upon 18 gamma w d square d1 square into g minus 1 by mu. This is the settling velocity expression, right? Mu is the dynamic viscosity and gamma w is the unit weight of water. But in place of dynamic viscosity, we know the kinematic viscosity. So kinematic viscosity nu is equal to mu by rho w. Now you can use this expression and convert this expression in terms of nu. So how to do this? So Vs1 is equal to 1 upon 18. This gamma w can be written as rho w into g into d1 square into g minus 1 divided by mu. Now this mu into rho w, this will be nu, right? So you can substitute the value of nu to get the settling velocity. So I'll just write down this new expression. Vs1 is equal to 1 upon 18 g into d1 square into g minus 1 divided by nu, right? Now you substitute all the values. You know the value of Vs1, you know the value of nu, you know the value of g, capital G, small g both. You can get the value of d1 square. The only catch in this question is the substitution of units. If you do not take care of the units, 100% you will make a mistake in this question, okay. So now just substitute all the values. So Vs1 in meter per second we have calculated this 16 divided by 3600 into 24. So Vs1 is 16 divided by 3600 into 24 is equal to 1 upon 18 g 9.81 d1 square that I need to calculate. Capital G is given as 2.55, I think. Capital G is how much? Capital G is how much? Okay. Okay, specific gravity of the settling particle is 2.64. Sorry, this is 2.64. Capital G is 2.64. This is 2.64 minus 1 divided by mu. And mu we have already calculated in meters square per second, which is 1.01 into 10 raised power minus 6. So this is 1.01 into 10 raised power minus 6. Now whatever size of particle you will get from here will be in meters. You quickly calculate the size of particle in meters, d1. Just solve this and get the size of particle in meter. Okay, I'll solve with you. So this is 16 into 18 divided by 3600 divided by 24 multiplied by 1.01. Okay, then divided by 9.81, then divided by 1.64, okay, multiplied by 10 raised power minus 6. You take the root of this answer. Okay, you just take the root of this answer and get the final answer. So this comes out to be, this D comes out to be, this D1 comes out to be 1.446 into 10 raised power minus 5 meters. This is the value of D. When you convert this meter into micrometer, you have to divide by 10 raised power minus 6. So micrometer is, okay, you have to multiply by 10 raised power 6. When you convert this meter into micrometer, you need to multiply by 10 raised power 6. So D1 is equal to 1.446 into 10 raised power minus 5 into 10 raised power 6 micrometer. Okay. So when you solve this, you will get the answer of D1 as 14.46 micrometer. And this is my final answer. This is the final answer. The size of the particle that will be removed with 80% efficiency is 14.46 micrometer. Okay. So I hope you have understood this solution. Let's continue with this. Let's solve this one. This is the question from disinfection. Again, I'll give you 2 minutes to solve this. And your time starts now. Okay, time's up. Let's solve this. This is the question from disinfection, and this question is framed from the Chick's law, where entire Chick's law is given to you. Question says that a wastewater is to be disinfected with 35 milligram per liter of chlorine to obtain 99% of kill. The number of microorganisms remaining alive after time t is nt. Means the number of microorganisms which are alive after time t is nt. Modeled by nt is equals to n naught into e raised power minus kt. Directly the Chick's law is given to you. Means number of microorganisms keeps on getting reduced while the disinfection is ongoing, right? After any time t, the number of microorganisms nt which are alive is equals to n naught into e raised power minus kt, where n naught is the number of microorganisms at time t is equals to 0 and k is the rate of kill. Next, the wastewater inflow rate is 36 meter cube per hour. The discharge which is entering into the disinfection unit, it is given as 36 meter cube per hour, and this rate of kill k is given as 0.23 per minute. If the depth and width of the chlorination tank are 1.5 meters and 1 meter respectively, the length of the tank rounded off to 2 decimal places is, okay. So basically width and height of the disinfection unit is given to you. You need to calculate length of this unit, right? If anyhow you know the volume of the tank, then using these 2 dimensions you can calculate the third dimension. So let's start with this question. First of all, you know the width of the tank and you know the depth of the tank. If anyhow you can calculate the volume of the tank, then using this volume you can calculate the length of the tank, right? The length of the tank can be calculated. Now this volume of the tank is equal to discharge which is entering into the tank multiplied by the detention time Td. Td is the detention time or retention time. Now what is this detention time? This is the time for which water stays inside the disinfection unit. If anyhow we can calculate this detention time, then we can calculate the volume of the tank. And what is this detention time? This is the time for which water is staying inside the disinfection unit. Okay. Now how to calculate this? In the question it is given that 99% of kill is taking place. Means the efficiency of disinfection is 99%, right? So the time taken by the disinfectant to make the number of microorganisms remaining in the system as 0.01 times of n naught. And that is what we mean by 99% kill. Means after time t, the number of microorganisms that are staying in the system alive is only 1%. And this much amount of time we should provide from our side for disinfection in order to have 99% efficiency of kill. Okay. So the number of microorganisms that are staying alive in the unit is only 1%. And 1% of what? 1% of originally present microorganisms. So directly you know Nt is equals to 0.001 times of n naught. Okay. Now use the Chick's law. Nt is equal to n naught into e raised power minus kt. And this time t is the time in which 99% kill of the microorganism is happening. And what is this time? We will calculate from this. So from here we can calculate the ratio of Nt by n naught. This is equal to 0.01 and this is equal to e raised power minus 0.23 into t. Since the value of k is 0.23 per minute, the time calculated will also come out in minutes. So from here you can calculate the time for which the water is staying in the disinfection unit, and this time is nothing but the detention time, right? This is the time that we are providing so that 99% of the kill can happen. Just calculate this. I will calculate with you. Just calculate this. So this time comes out to be 20.02 minutes. This time comes out to be 20.02 minutes. Now we know the detention time, we can calculate the volume of the tank. The only thing is, please keep a check on the units. Discharge is given in which unit? Discharge is given as 36 meter cube per hour. So the detention time that you have to keep should also be in hours. So we will do like this. So volume of the tank V is equal to discharge multiplied by the detention time. Discharge is given as 36 meter cube per hour. This is 36 meter cube per hour. So detention time is 20.02 minutes, and this minutes converted into hours, you need to divide by 60. So now this will also be in hour. This hour and this hour will going to cancel out, and you have the volume of the tank in meter cube. Just do this calculation. So this is 36 into 20.02 divided by 60. So this comes out to be 12.012 meter cube. I'll just cross check this. So this is 20.02 divided by 60 into 36. Yeah, 12.012 meter cube, right? Now you know the width of the tank. The width of the tank is how much? The width of the tank is 1 meter and depth of the tank is 1.5 meter. Width of the tank is 1 meter, depth of the tank is 1.5 meter. Now using this volume, you can calculate the length. So volume is equals to length into breadth into height. Volume is 12.02012. This is equal to L multiplied by width 1 into height 1.5. From here you can calculate the length, and that length comes out to be, so this is 12.012 divided by 1.5. So this comes out to be 8.008. This length of the tank comes out to be 8.008 meters. Right? This is the length of the tank. Okay. So these are some of the questions that can you expect in GATE 24. These are the prominent areas from where the questions are regularly framed in GATE examination. We have this Telegram group link in the description box. You can join our Telegram group for regular quizzes. You can check onto our website for registering into the zero fee program, where we are not charging you a single penny and giving you video content and question papers and a lot of things. You can check on the zero fee program. All the things are mentioned in the description box, right? So for this session, I hope you found it useful. You found it more kind of content, right? You have found it a lot of new things that are there. So thank you so much. I'll see you in the next session for environmental engineering. So for today, that's all. Thank you so much.